Alright guys, so we have pretty much come to the end of the class. This will be the final video. Today we're going to cover a topic that I think is kind of a fun one. And normally in class I would sit down at the dot cam and I would just use blank sheets of paper to go over this topic. So that's what I'm going to do here. So the only thing I'll need today is just a blank sheet of paper. And we're going to go over this topic. And the topic is going to be Lewis structures. Okay, so how do we represent molecules? How do we draw them? Okay, and within this topic, I can cover a few things. So we're going to cover everything from actually drawing the Lewis structure to what is a polar compound, how to identify a polar compound, and sort of get into organic. Okay, so that's how far we're supposed to get in this class. So I can kind of cover all of those with just a blank sheet of paper. So let's start that now. Okay, so I'm just going to sort of walk through some examples here. Okay, so we're going to start with just a very simple molecule. Okay, so we're going to start with just H2, so hydrogen gas. So how would we represent this if we were going to draw it? Okay. So the first thing we have to do is we have to understand what it is that we're doing. Okay, so we're trying to give a visual representation of this molecule. And the first thing we need to know in order to do that is we need to understand how many hydrogen brings to the table. So each hydrogen, so if you think about its valence, okay, so it's our first element on the periodic table. So its valence is just 1s1. Okay, so it only has one electron to give. Okay, so I'm just going to represent electron as E negative. Hopefully, you guys are used to that by now. Okay, and I have two of them. Okay, so my total electrons are going to be 1 times 2. And obviously, we don't really need to write this out, but just for visual purpose. So I'm going to have a total of 2 electrons, or in other words, 1 pair. Okay, so that's where we have to start from. Okay, so if we were to just draw an individual hydrogen atom, we maybe could draw it something like this. Okay, and just represent its 1 electron with a little dot. Okay, so I'll just make a note here. This is our electron. Doesn't want to let me write right there. Let's do this. There we go. Okay. So, and then we could draw a second one over here. Okay, so maybe something like this. Now, obviously these two atoms are bonded. Okay, so how are we going to represent that? Well, we're going to represent them with a line like this. Okay, so anywhere you see a dashed line, that represents 2 electrons. Okay, so this and this are essentially equivalent. Okay, but it's much more visually appealing to just use a dash. And then in places where we don't have a bond, we still represent electrons with 2 dots in this way. Okay, and we call that a lone pair. But we'll get to that in just a minute. Okay, so how are we going to show someone else that within H2, I have 2 bonded hydrogens? How would I represent that? Well, you would do something like this. So I just draw 1 hydrogen, draw the other one at a reasonable distance next to it. Okay, and then like I said, we're going to represent bonds, covalent bonds, with a dash. So there you go. Okay, so this tells me and tells someone else that within this molecule, I have 2 hydrogens bonded together. Okay, so that's just a very simple base example, but that's essentially everything involved with drawing Lewis structures. Aside from, there's some other things you need to know, but that's basically it. Okay, and like I said, I'm just going to use some examples to sort of illustrate all these different ideas for you. Okay, so that's our first example. Okay, let's try another one. Okay, so we'll pick out another familiar molecule. And I have 15 or so examples here, and we'll walk through them and see how long it takes us. Okay, so my second one something else we've talked about a lot in this class. Just water, plain old water, H2O. Okay, so a little more complex than just simple H2. Okay, but we're going to follow the same process. So the first thing we have to do is we have to count up our electrons. So we want to know how many total electrons, valence electrons, do we have in water. Okay, so let's start with hydrogen. Again, hydrogen has just one electron. Okay, and I have two of them. Okay, I'm going to say plus whatever oxygen brings. Okay, so oxygen brings, if you pull out a periodic table and you count from the left, you count its valence. So it has 1, 2, 3. So let's just write out its valence. So oxygen would be 2s1, 2s2, and then we come over to our p. So 2p. Okay, and it has 1, 2, 3, 4. So 2p4. So in total, oxygen brings 6 electrons. So we have a total of 8 electrons. Okay, so that's how many electrons we should have in our structure. Okay, so this is a total of 4 pairs. Okay, so the next thing we need to do here is, since now we have more than just 2 atoms, we have to decide which one goes in the middle. And with water, we know the structure, of course, so it's not that difficult. But suppose we didn't. How will we decide this? Well, one thing we have to learn first is that hydrogen only accepts one bond. So anytime you have a hydrogen, you're only going to want to put one bond to it. And that's because it's basically completely full. Okay, you can kind of think of it that way, with just 2 electrons. Okay, so in other words, hydrogen we know is not going to be our central atom. So our central atom will have to be oxygen. Okay, and so if you're going to draw the structure for water, I would just put oxygen in the middle, and then maybe just put our hydrogens on each side. Okay, we wouldn't want to do this. We wouldn't want to, for instance, put our second hydrogen over here. Okay, that doesn't make any sense. Okay, because now we have a hydrogen with 2 bonds. Okay, so that's not right. Okay, so let's go back with what we originally did. Okay, and now we can go ahead and draw in some bonds. So there's a bond, there's a bond. Okay, now we can count how many electrons we've used. So we've used 2 here and 2 here. So we have 4 left over. Okay, well the only place we can put them is on oxygen. So we're going to put those as lone pairs. Okay, and we do that just by filling in dots like this. Okay, so now if we count up, we've used 2 here, 2 here. So we've used all 8. And if you notice, we've used 1, 2, 3, 4 pairs of electrons. Okay, so that's all of our electrons. Now, you could represent water this way. Okay, but in all reality, you would want to draw something more like this. Okay, this is a more accurate drawing. Okay, because this is going to be sort of a bent molecule. Okay, so and the reason for that is because we have these electrons here, and they essentially act huge, right? So that they're bigger than life. They're bigger than normal. Okay, so they sort of displace those hydrogens down. But they're going to want to be on one side of the molecule. So this is the way oxygen really would look if you were to draw it out. Or, excuse me, water. Okay. And we'll come back to this idea later. But so the next thing I want to talk about is, once you have a structure like this, how do you know that it's a reasonably good structure? Well, one way you can know that is called the Octet Rule. Okay, and this rule tells you that you want to have 8 electrons around most atoms. Okay, so if we were to count up the electrons that oxygen can see, okay, so remember that these are covalent bonds, so we're sharing electrons between the 2 atoms. So the amount of electrons it can see, 2, 2, 2, 2. Okay, and if you add those up, it's a total of 8. Okay, that's our rule. So oxygen wants to see 8 electrons, and it can. Okay, so this is probably a reasonably good structure. And if you might be thinking, well, what about hydrogen? Why doesn't you don't have 8 electrons around hydrogen? And you're right. So the reason I said most atoms It's because hydrogen is a special one. And the way that it's a special one is that it only wants to see 2 electrons. So we call for hydrogen, we call it a duet. Okay, so it only wants to see 2 electrons. And there are some other atoms that are this way, but none have as few as hydrogen. So it's going to be only 2 electrons. Okay, so to be satisfied, hydrogen only needs a duet. Most other atoms, though, need an octet. Okay, so we'll look at some more examples of that. Okay, so I'm going to pull this up, give us some new space. Okay, so let's look at a more complex sample. Okay, so let's go to C2H6, so ethane. Okay, just a nice unsaturated carbon organic molecule. Okay, and when we talk about organic molecules in chemistry, we're not talking about organic in the same way that you would, say, find it at the grocery store. When we talk about organic molecules in chemistry, we're talking about things that only contain carbon, hydrogen, oxygen, nitrogen, and then occasionally sulfur, phosphorus, and maybe a few others. But generally speaking, if we're talking about organic molecules, we're talking about things that only contain carbon, hydrogen, oxygen, and nitrogen. Okay, so that's what we talk about when we talk about organic molecules. Okay, so we have a nice organic molecule here, ethane. Okay, so suppose we wanted to draw a Lewis structure for this. We're going to start the same way every time. We're going to figure out how many electrons we have, how many valence electrons we have. Okay, and then from there we can start to determine what should our central atom be and what is a reasonable structure. So the first thing, we need to count up our electrons. And to do that, remember that we're looking at valence electrons here. So we're always going to do this the same way. Okay, so you don't have to write out your electron configuration every time, but I think it's helpful when you're first learning because that way you can really see what we're talking about. So for carbon, if we write out its valence, it's going to be 2s2, 2p2. Okay, so for a total of 4 electrons. Hydrogen, we know, just brings 1, so it has 1s1. Okay, so it only brings 1 electron. Okay, so now we need to figure out how many total we have. So we're going to say 2 times 4 electrons plus 6 times 1 electron. Okay, and this gives us a total of 14. Okay, so now we need to determine our central atom. And since we know hydrogen will never be the central atom, okay, unless we're only talking about H2, okay, so we know it's going to be a carbon. So it's difficult because I know this structure, okay, but if you were just to take a reasonable guess, just try sketching out your atoms, and you don't have to stick with it if you're wrong. Okay, but let's put the 2 carbons next to each other because they're the only thing that can have more than 1 bond. And then maybe we just fill in your hydrogens around it. Okay, just evenly spaced around the molecule. We're not going to put them here, okay, that doesn't make any sense. Okay, so we would have to put them over here maybe. Okay. So next thing, you want to fill in your bonds. So we know each carbon and hydrogen are going to get 1 single bond. So that's done. And now we need to put 1 in the middle to connect the 2 carbons. I'll make that a little bit better. Okay, let's make this a longer one. And now we need to first check our octet around our carbons and our hydrogens. Okay, so here we have 2, 2, 2, 2. Okay, so a total of 8. So our octet is satisfied for carbon, for this carbon, and then each of our hydrogens have a duet, so they're satisfied. Okay, so we're happy. And if we check the other, we would find the same thing. Okay, now we need to count up our electrons. So we have 2, 4, 6, 8, 10, 12, and then in the middle, 14. Okay, and we said we had 14 to use, so we're good. Okay, so this is probably a reasonable structure. And the reason I say reasonable is because there could be more than one possible structure. If all I give you is a chemical formula and no other information, Okay, you don't necessarily know what the structure could be. Like if, for instance, this was, I don't know, C3 for some reason. You know, there's such things that can exist where we have 3 carbons in a triangle. Okay, so, or I could also have 3 carbons in a line. So if you don't have more information, you can only come up with reasonable structures. And as long as your octets are satisfied, things like that, then you can say it's probably a reasonable structure. Okay, so let's move on to another example. Now let's throw another atom into the mix. Okay, what if we had CCl4, so tetrachloride? Okay, so now we have chlorine instead of hydrogen. Okay, no, but no big deal. Okay, we're going to approach this the same way. So we know that carbon brings us 4 electrons. Okay, and some of these things you'll just get to know. If you go on to take organic chemistry, you're going to draw so many structures. This will become so second nature to you. You won't even have to think that carbon, how many electrons does carbon have. Okay, and we know that each chlorine, if you look at its valence, okay, and you can either count these from your periodic table or write out the valence, okay, if you're not sure. But we know each one is going to bring 7 electrons. And there's 4 of them. Okay, so this gives us a total 32 electrons, or in other words, 16 pairs. And sometimes it's helpful to know how many pairs of electrons you need. Okay, so just like I told you that hydrogen will almost never be the central atom, pretty much never. I can't really think of one. Okay, well, the same thing is kind of true with your halogens. Okay, so your halogens will also never be the central atom. So that only leaves us with one choice, which is carbon. Okay, carbon's a great central atom. It's always a good place to start. Okay, then we have 4 chlorines, so let's just write them evenly around the molecule. Okay, because this is the way atoms or molecules tend to behave. They typically want to maximize the distance between atoms. Okay, or maximize the distance between electrons. So remember, they're repulsive. You know, they have the same charge. Okay, and then let's just fill in single bonds between each chlorine and carbon. Okay, and so we've used 4 pairs. So let's say minus 4. So we have 12 left. Okay, but where can we put them? We can't put any more on carbon. You wouldn't want to do this. Okay, that would cause us to have an ion, but we don't have a charge. Okay, well, something that's interesting about things like your halogens is they tend to take on this sort of configuration, where we have 3 lone pairs and a bond. Okay, so if we count up our octet now, 2, 4, 6, 8, and then around the carbon, 2, 4, 6, 8. Okay, so that would satisfy both of them. Okay, so we've used 1, 2, 3 more pairs. Guess we're down to 9. Okay, well, guess what? We have 3 chlorines left. Doesn't want to let me draw up there. Okay, so we have 3 chlorines left. And we have 9 electrons. They each get 3 lone pairs, so guess what? That math works out. Okay. Okay, so this is what a reasonable Lewis structure would be, because they all have a satisfied octet. We've used all of our electrons, so if we count these up, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and that's how many we said we had. Okay, so we've used all of our electrons. Okay, so all of our octets are satisfied. So this is a reasonable structure. Okay, and this is one thing you have to get used to, is counting the electrons and, you know, coming up with reasonable structures. Okay, let's take a look at another example here. So similar molecule. So let's do C2. Let's do H4 this time. So ethylene. Again, we know each carbon brings 4. Okay, so 4 electrons times 2 plus 4 times 1 electron. And it doesn't really matter which order you write these in, as long as you get the total correct. Okay, this will be 12 electrons, or in other words, 6 pairs. Okay, so think back. If we think back to C2H6, we drew a structure like this. Okay, and we filled in our hydrogens around like this. Okay, and this is going to have a similar structure. Okay, but the thing that's going to change here, because if you count up your electrons here, 2, 4, 6, 8, 10, 12, 14, okay, it's 2 electrons too many. Okay, and we also have 2 hydrogens too many. So what we're going to do to go from C2H6 to C2H4, you're going to remove 2 hydrogens, okay, obviously. Okay, and that also gives us another 2 electrons less, 2 fewer electrons, but it also gives us 2 electrons to move somewhere else. Okay. And if we count now our valence, or our octet for each of these, 2, 4, 6, 2, 4, 6, and then each of the hydrogens are satisfied, of course. Okay, so each one only has 6 in its octet. Okay, obviously they want 8. So the way that we're going to remedy this, okay, we're going to change this bond in the middle. And we're going to change it to a double bond. Okay, now if we count 2, 4, 6, 8, 10, 12, which is what we said we could have. And now let's count our octet. 2, 4, 6, 8. So 2, 4, 6, 8. Because again, remember, each of these lines represents 2 electrons. And remember, they're being shared by each carbon. Okay, so they each are seeing 8. 2, 4, 6, 8. Okay, remember our octet rule? Okay, so that's satisfied. So this is a reasonable structure. Okay, and normally we would draw it more like this. Okay, you would kind of space out your hydrogens a little bit, like this, at an angle. Okay, either structure would be correct. Okay, but if you saw an organic chemist draw this, they would draw it more similar to what I just drew. Okay, but either one would be correct. Okay, so that's ethylene. Okay, and if we did this, so if we instead said C2H2, okay, so ethine. Okay, now we're going from, so again, we're going to put our 2 carbons, but now we only have 2 hydrogens. So we're going to put them, we could put both here, okay, but that's probably not right, okay, based on our other 2 examples. Okay, so we'll put them here. Okay, but now each carbon's only seeing 2, so we have 8 plus 2 gives us 10 electrons. Okay, so we have to figure out how each carbon can still see 8 electrons if we only have 10, right? That's seems like it would be pretty difficult to do, right? But the way we're going to do this is we're going to put a triple bond in the middle. Okay, so now I have 2, 4, 6, 8 on both carbons. Okay, so just for convenience here, I'm going to draw out one of our original structures we did, ethane. And so this is where the little bit of organic chemistry comes in, aside from just drawing Lewis structures. Okay, so this is ethane. This would be ethene. Notice the endings. And this would be ethine. Okay, so if we have single bonds, we go with the ending ane. So these are called alkanes. So we go from alkane. Looks like a LC, doesn't it? But it's a K. Okay, then if we have a double bond, we add ene. So that's an alkene. Okay, and if we have a triple bond, we add ine. So that's an alkyne. Okay, so with no other information other than the name, so if I told you this was ethine, with no other information, you would know that it had a triple bond. Okay, so that's just some basic terminology that you'll see when you get to organic a little bit more. Okay, so now let's add even another new element in. Okay, another new atom. Got a blank page for us. And I'll post these just like I have the others for you guys to look over if you need to. So let's look at this one. Right, HCN. So 1 carbon, 1 nitrogen, 1 hydrogen. Okay, so this is going to be 1 plus 4. The nitrogen gives us 5. Okay, so a total of 10 electrons. Okay, so one thing we know right away is that hydrogen will not be the central atom. So let's just write out hydrogen. Okay, we know it's going to be off to the side somewhere. Okay, with this particular structure, it might not be immediately obvious how to pick the central atom. Okay, so this is one of those things that comes with a little bit of experience, okay, a little bit of knowledge about the molecule itself. Okay, but let's try carbon. Let's just put carbon there. Okay, hydrogen and carbon, they like to stick together. They're friends. Okay, and then we have one atom left, which is nitrogen. So we'll put it over here. Okay, so now let's just put a single bond there. Okay, remember we have 10 electrons to split between 3 atoms. Okay, hydrogen only needs 2, so it's fine. Okay, but we can just see right away that carbon and nitrogen aren't happy. Okay, so if you remember back to ethane, one way we solve this, we could put a triple bond here. Sure. 2, 4, 6, 8. Okay, so now carbon octet is happy. It's fine. Okay, but now nitrogen is only seeing 6. And we still have 2 electrons left over. Okay, so what we can do is we can put those here as a lone pair. Okay, if we count them, 2, 4, 6, 8, 10. Okay, and the octet for nitrogen, 2, 4, 6, 8. Okay, so everybody's happy. So this is probably a reasonable structure, and it's the correct structure, at least for what I'm talking about here. Okay. And now we can use this molecule to talk about something else. Okay, but first let's bring water back. Okay. What I want to talk about here is polarity. Okay. So polarity basically is talking about polar molecules. Okay, so this word polar. So you've heard maybe polar opposites means they're exact opposites, extreme opposites. Okay, so polarity is kind of a similar term. And basically, if you want to look for want to see if a molecule is polar or not, what you want to do is you want to look for electronegative atoms. Okay, so you want to look for things like oxygen, fluorine, chlorine, any of your halogens. But things up in the right-hand corner, so remember electronegativity goes in this direction on the periodic table, so fluorine is our most electronegative atom. Okay, so you're going to look for these atoms in the molecule, and we could even include nitrogen in this as well. Okay, so you're going to look for these atoms, and if they're off to sort of one side, if the molecule seems lopsided, that's going to be a polar molecule. And the reason that is, okay, so if we just look at our example of water here, let's take a look at water. So what we can do is we can determine if we have any what we call dipoles. And a dipole just means a place where you have an uneven sharing of electrons. And we represent it this way. So comparing hydrogen and oxygen, well, we just said oxygen was one of our electronegative atoms. Okay, so right away, you know something's probably happening there. Okay, and the way we would represent this, I'm going to grab a different color. Let's go green, why not? Okay, the way we're going to represent this is with an arrow, okay, that has a cross on one side. And you're going to put the plus sign or the cross, whatever you want to call it, towards the more positive atom or element. Okay. And you're going to point the arrow towards the more electronegative atom. Okay, so in this case, towards oxygen. Okay, and you could do the same thing here. Okay, and if you have a situation like this, where we have all of the arrows pointing essentially in the same direction, we can draw an overall dipole. Okay, so for the whole molecule, we could draw this dipole. Okay, what this tells us is that we have a polar molecule, and we of course know water is a polar molecule, right? It's our polar, one of our classic polar solvents. Okay, so we know it's a polar molecule. Okay, so our assessment we know already is correct, So, but this is how we determine this. So if we take a look at now at our HCN over here. Okay, so what are we going to find in this? So we're going to find hydrogen, carbon, and nitrogen. So remember we said hydrogen, hydrogen is not really going to be electronegative in any way. Carbon is not one from our list. It may be more electronegative compared to some things, but in this case, it's not really what we're looking for. But what we do see, we see nitrogen. Okay, nitrogen is right next to oxygen, right next to fluorine. Okay, right next door. Okay, so this is going to be our electronegative atom. So if we wanted to draw a dipole, we would say that this is probably a polar bond. Okay, so remember, point the arrow towards the more electronegative atom. Okay, so our overall dipole for the molecule, if we wanted to draw it, so we could draw it up like that, but most of the time you'll see people do this. You'll see people draw it through the atoms like this. Yeah, so that would be your dipole. So you would know that this is a polar molecule. Okay, let's bring out another example. So let's take a look at one we showed earlier. So CCl4. I'm just going to go ahead and redraw the structure for us. Okay, still talking about polarity. Okay. So, what if we wanted to decide whether this is a polar molecule or not? Well, first thing we're going to do, again, just write in your dipoles. So chlorine is going to be one of our electronegative atoms. Okay, so we know that there's probably going to be dipoles near the chlorines. Okay, so let's go ahead and draw this. So compared chlorine to carbon, chlorine would be more electronegative. So we could draw this. Or we can draw that all the way around. Okay, so all four of these bonds are going to have these little dipoles. Okay, and you may see this from time to time. So a lowercase delta and a minus sign. So each of these would be partially negative is what this denotes. Okay, so a lowercase delta means that it's partial. So we're talking about partial charges. And in the center, since we all have all these electrons being pulled away, we can draw a partial positive here. Okay. So if we take a look at this and we wanted to answer the question, is this polar? Okay, well, we see dipoles, so that means it's polar, right? Well, not exactly. Okay, so since they're all pulling away from the center, in other words, we have sort of equal forces pulling in all directions, this would be a nonpolar molecule. So no, this would not be a polar molecule. So remember, to be a polar molecule, we have to have some lopsidedness. So this would be polar. Okay, we have to have some side of the molecule. So my partial would be here, partial negative, partial positive, partial positive. Okay, so we have to have some pull towards one side. So you can almost think of it like the molecule's heavy. Okay, so if you set it down or if you tried to balance it, it would fall over. Okay, so you could think of it like that. So it's almost like it's electron heavy. Okay, so if we have some side that's heavy like that, that's going to be a polar molecule. Okay, but if you have something like this, where I have the same pull in all directions, that's going to be nonpolar. And if we sort of look at one of its cousins, maybe, you could say, so dichloromethane, this is a polar organic solvent. Okay, so it's got chlorines off to one side like this. And now if we draw in the dipoles, let's grab another color. Let's do purple. Why not? Okay, so if we were to draw in our dipoles here, so you would have something like this. Okay, but now, since we have only hydrogen on the other hand, okay, there's not going to be a dipole there. But overall, we have a partially positive carbon. Okay, so we could draw an overall dipole like this. Okay, so this would be a polar molecule. Because it sort of has that pull off to one side. Okay, so these two are like kind of similar cousins here. So I think they're good for comparison. Okay, but these would be example of a nonpolar and a polar molecule. So this would be our nonpolar. And usually you'll see it written with a dash like that. Not always. Sometimes people will crunch it together. Whichever way is fine. Usually you'll see it with a dash. But okay, so those two examples hopefully that illustrate that idea well. Okay, so one more thing in line here talking about our polarity of molecules. Let's look at one more. Okay, so let's look at an alcohol. Okay, so let's go with, I don't know, we'll say, let's just look at methanol. So CH4O. And a lot of times when you see alcohols written out, you would see this CH3, our methyl group, and then our alcohol group. Okay, so anytime you have an OH, that denotes you have an alcohol. So one thing when you, if you go on to organic chemistry, one thing you'll learn is that actually it's sort of equivalent to taking a language class almost. Okay, just as much as it's taking a science class. Okay, and one reason why is you're going to learn a lot of what we call functional groups. Okay, one of those functional groups is an alcohol, so an OH group. Okay, so this would be methanol. So I'm just going to go ahead and draw out the structure. Okay, so it would look something like this. Okay, and hopefully you would be able to come up with this on your own. Okay, so this is our structure for an alcohol. Okay, so this is methanol. Okay, so, and continuing sort of talking about polarity here, let's take a look at any dipoles we could draw on this molecule. Okay, so certainly if we compare something like carbon to oxygen, okay, we know that we're going to have a dipole something like this. And it's true that you would have one here as well, but to a less extent. Why to a less extent? Well, there's simply less electrons to share there, so there's less to pull away. And so the way that we would represent this is you would represent it, I'm going to try to draw as small as I can with a very tiny little arrow. Okay, so that would represent a small dipole. Okay, and generally speaking, we probably wouldn't draw this one. Okay. Okay, and so overall, if we wanted to draw the dipole for this molecule, we would say it looks something like this. Okay, so the dipoles can take on, I guess the point I'm trying to make here is that dipoles can take on, a few varieties, a few shapes, and there's certain things that when you see them right away, you'll start to recognize it. Like if I have an alcohol group off to one side on a molecule like this, then I know it's going to be polar. On the other hand, if I had something more like, I don't know, this is not a real molecule in any way, but if I had something like this maybe, okay, then I would have opposing dipoles. Okay, so I would have this. So they would be back to back like this. That would not be polar. Okay, but as it stands, okay, that would be a polar molecule. And like I say, some of these things you'll start to recognize and you won't even realize you're doing it. Okay, like for instance, knowing that carbon brings 4 electrons, oxygen brings 6. You're going to do this so much when you get into that class. You're going to be so quick at it that you really won't even have to think about it. Okay, so now that I've sort of shown you some of the basics here, I'm going to give you some examples, more examples, but examples you can try on your own. Okay, so let's make a new page. Okay, and so the rest of this, I'll just be writing a formula, and then you can try to see if you can come up with a Lewis structure on your own. Okay, and then I'll draw out the correct structure for you, and you'll know whether you did it right or not. Okay, so the first one here, let's do this. So we're going to jump to a bigger molecule here. So C6H14. Okay, so give this one a try. Count up your electrons. Okay, then go ahead and pause the video. Try to draw this one out. And then when you unpause it, I'll have the solution for you. Okay, so this would be our solution. Okay, so we just have an alkane chain. So this would be, we would call this a chain alkane, or a long chain alkane. Maybe not a long chain, but you know what I mean. So this would just be a straight chain alkane, something like that. In other words, because it's not branched at all. Okay. And hopefully you're able to come up with this. Notice one thing here that I think is important to point out here. Notice carbon always has 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. So you end up with these CH3 groups on the edges, and then CH2 groups on the interior. Okay, and that's pretty much always going to happen unless you have some other atom there. Okay, but if you just have carbon and hydrogen, this is what you're going to end up with. So you're going to end up with, we call this a methyl group. Okay, so the CH3, this would be a methyl group. Okay, and then, well, that's, and if we had something like CH3, CH2, and this was connected to something, this would be an ethyl group. Okay, so just sort of taking things like ethane, methane, and just chopping that ending off and switching it around. Okay. Well, those are more, again, more things you'll learn in organic if you go into it. Okay, so hopefully you came up with a solution. So let's look at a similar molecule. What about C6H12? So all we've done, we've pulled away 2 hydrogens. Okay, give this one a try. Okay, so hopefully you've had some time to work on this one now. And you might have come up with something like this. 1, 2, 3, 4, 5, 6. So you might have tried to draw this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then you would run out of hydrogens. Okay, so in this case, you would have 2 options. Okay, without more information, it would be difficult to determine which option was correct. So one option, okay, so first of all, you have to count out your electrons. So 6 times 4 is 10 plus 12. Okay, so you have 22. So 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, this is not 10. I did 6 plus 4. That's not right. 6 times 4 would be 24. Starting to say that doesn't seem right. So 36 electrons. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so we still also have some electrons here that we can deal with. So you could do something like this. So you could start adding in some double bonds, but if you keep playing with this, so maybe you put one here, but if you keep doing this, okay, you'll realize that there's no way to make this the correct structure in terms of a chain. Okay, and while we're talking about this would be a good time to point out that, well, we'll get to that next. Okay, so you'll find there's no way to make this a chain. So one other structure we have in organic chemistry that we see a lot are rings. Okay, so anytime you have carbons bonded in a circle like this, we call it a carbon ring. Okay, and then, okay, so we have 6 carbons in a circle, in a ring. So they all have 2 bonds. So here's a bond and here's a bond. Okay, so they can all take 2 more bonds. And we have 12 hydrogens, so guess what? Right, they're going to go like this. Okay, so C6H12 is going to look something like this. Okay, and one thing you'll start to recognize right away with these kind of structures is that if it's C6H12, okay, it's going to look like this. We have 2 hydrogens on each carbon. Okay, with that being said, what if I gave you this structure or this formula, C6H12? H6. Okay, so see if you can draw this one based on that information. Okay, so if we have this, again, we have only 6 hydrogens and we have 6 carbons. Okay, so kind of right away that should kind of jump out at you, and maybe not quite yet, but eventually that will kind of jump out at you as being a structure like this. And then you're going to put a single bond to each of those. Okay, so you're not going to double them up, but you're actually going to put them like this. And there's probably other structures you could come up with that would be reasonable. Okay, but this is the one specifically I had in mind. Okay, now if you were to count the bonds around each carbon, you'd see there's only 3. So how can I remedy this? Well, this is where I start to add my double bonds in again. Okay, so each carbon has 4 bonds. Okay, this is a benzene ring. Okay, without more information, it might be a little bit difficult to determine that. Okay, but based on sort of some background knowledge here and kind of the progression we went through, hopefully you were able to come up with something close to this. Okay, so this is about experimentation. It's about putting the atoms together and seeing, can I draw a reasonable structure? Can I fill my octet? Okay, we call this a supercarbon. Okay, if you do something like, you have all kinds of crazy bonds. Okay, we call this a supercarbon. It has graders. Okay, so don't make supercarbons. That doesn't exist. Okay. But it's just all about experimentation, and I wouldn't expect you to be perfect at this, but it's something that if you go onto organic, it's something you need to get good at, and it's something you will get good at. Okay, so the last topic I want to talk about before I end this is I just want to talk about, okay, what about ions? What about charge? Okay, so everything we've looked at so far has been neutral. What about things that have charge? Obviously, we know that there are charged atoms that exist in the world. Okay. So how do they come into play? Okay, so without saying anything else, I would like to give you this structure, this formula, H3O plus, should be familiar. Okay, from our discussions, talking about acidity. Okay, so see if you can draw a structure for this, just based on what you already know, and see if you can put the charge in the right place. Okay, so the first thing we want to do, count up our electrons. So 3 times 1 electron. Then we know, of course, that oxygen gives us 6. Okay, this gives us a total of 9 electrons, but we have a +1 charge. Okay, so we're going to subtract 1. So we have a total of 8 electrons to play with. Okay, we know hydrogen's not going to be our central atom, so let's just draw oxygen here. Okay, and let's, just like if we were drawing water, let's space out our hydrogens. Okay, let's put some bonds. Okay, so if we count up our octet around oxygen, we have 2, 4, 6. Okay, so not quite enough for its octet, and we'll have only used 6 electrons as well. So we still have 2 more, and those are going to go as a lone pair. Okay, so now the last thing we need to do, so we have 2, 4, 6, 8 electrons, so its octet is happy. But we see this big plus sign over here. Okay, so we know this is supposed to be a charged molecule. So what our job now is to figure out where those charges are, or what the charge is. There can be even more than one sometimes. Okay, and the way we're going to do that is you want to break each bond so that it's sort of like split in half. Okay, so when it comes to looking at charge, for each bond, you're only going to count 1 electron. Okay, so if we look at the charge around oxygen, or the electrons around oxygen, so we have 1 here, 2 here, 3 here, 4, and 5. So it's only seeing 5 electrons. And if we go back to its valence, so we have 2s2, 2p4. Okay, and this is a total of 6 electrons in its valence. So if an atom doesn't have a full valence, in other words, if we remove an electron, we're creating a charge, okay? Or causing a charge to occur is probably a better way to say it. And if we remove electrons, it becomes positive. If it has extra electrons, of course it becomes negative. Okay, so if we were going to draw a charge onto this molecule, you would put it on the oxygen. So you would do this. You would just say plus, and then you would put a circle around it. It's traditional to put a circle around charges so that they're easy to see, and so that you know that they're not some other part of the molecule or something like that. Okay, so H3O plus would have its charge on the oxygen, simply because it only has 5 electrons where it could hold 6. Okay, so a normal oxygen atom would have 6 valence electrons. Since it only has 5, it's going to be positively charged. Okay, so let's try another one. So a similar idea here. So what if we try SO4, so sulfate polyatomic ion. Okay, see if you can come up with a structure for sulfate. Okay, and just remember with this one, again, we have to have a charge. Okay, so if you count up all your electrons, okay, so sulfur going to be similar to oxygen, going to bring 6. So essentially what you have here is 6 times 5, okay, which gives you a total of 30 electrons. Okay, so we've got 30 electrons to play with here. And without some previous knowledge, it might be a little bit difficult deciding a central atom for this. Okay, but if you notice one thing on your periodic table, sulfur is below oxygen, okay, which means that it has access to a few more orbitals than does oxygen. Okay, so we're going to need to put a lot of bonds to our central atom in this. Okay, so a good choice here would be sulfur. And that just sort of comes with intuition. Okay, so let's just space our oxygens around evenly around our sulfur. And let's just put a single bond, and let's see where we are. Okay, so stop and check is kind of a good method with this. Okay, so each oxygen here is only seeing 2 electrons. The sulfur is seeing 8. So the sulfur is happy in terms of its octet. Okay, we've still got a lot of electrons left, so we only used 8. Okay, so we still have a lot more left. We have, 22 left. Okay, we see that our oxygens are not quite happy. So let's do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. Okay, so if we add up all of our electrons now, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we've used two too many electrons. Okay, so we have to remove at least 2 from somewhere. Okay, we also don't have any charges. Okay, so we have 2 issues there. Okay, so if we haven't put charges in yet, is what I should say. So if we were to look at this and count our charge, remember again to split your atoms. Okay, like this. Okay, and you can add in your charges. So each oxygen now sees 1, 2, 3, 4, 5, 6, 7. Remember we said it had a valence of 6? Well, now it has this valence of 6 plus 1. So it's 7. So it has 1 extra. So each oxygen in this situation would have a negative sign next to it. Okay, but we don't have SO4 4 minus. We have SO4 2 minus. So how are we going to solve this? Well, first thing we're going to do is we're going to get rid of at least 2 of these minus signs. Okay, so let's just erase those and make them so that they're not charged anymore. Okay, but if I just remove those 2 electrons, now they're 1, 2, 3, 4, 5. Now they would both be positive. Okay, and now our overall charge on the molecule would be neutral. Okay, but we don't have a neutral molecule. Okay, so that's not right either. So what we have to do then, okay, we need to add in something else. We need to change something else about the molecule. And what that particular thing that we're going to change is, we're going to add some double bonds in. Okay, so we're going to keep our 2 negative charges there. Those are probably right. Okay, but let's see if we maybe add a double bond in. Let's see where we are. So what if we put a double bond here and a double bond here? So now let's count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So now we're at 32 electrons. Okay, one thing failed to mention over here, so hopefully you caught this, because remember before we had a positive sign and we subtracted it. Okay, but here we have to add 2 because of our negative charge. Okay, so actually we have 32 electrons. So actually our structure is not as bad as we thought. Okay, so we have 2 negative signs, so we have 2 minus charges. Okay, and let's check all our octets. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everything's happy. Sulfur, 2, 4, 6, 8, 10, 12. Okay, 2, 4, 6, 8, 10, 12. So it has more than enough. Okay, but individually it has 1, 2, 3, 4, 5, 6. Okay, it wants 6 in its valence, so it's completely happy. So this is actually a good structure. Okay, so we have all our charges covered. We've used all of our electrons. Nothing has crazy octets. Okay, the only thing that we needed to know for this particular one is that sulfur can have what we call an expanded octet. So anything phosphorus, sulfur, and those kind of atoms, a lot of times you'll see them with expanded octets or expanded octet valence, this kind of thing. Okay, so this is actually the correct structure for the sulfate ion. Okay, so a couple more examples here, and then I think we'll stop. Okay, so give this one a try. So based on your new knowledge that sulfur, phosphorus, these kind of things can have more than just 4 bonds. Okay, what if we draw this structure? Give this one a try. Okay, remember what I said about halogens. So give it a pause and give this one a try. Okay, so with this one, we know phosphorus is going to bring 6 electrons, plus we have 5 chlorines that are all going to bring 7 electrons from their valence. Well, I'm sorry here. I realized what I did wrong here. So phosphorus is actually only going to bring 5. Okay, because it's right there under nitrogen, which brings 5. So it's 5 in its valence. Okay, so if we add these up, we have 5 plus 35, which gives us 40 electrons to play with. Okay, and we have no charge. Okay, so we just have a neutral compound. Okay, and remember we said halogens are probably never going to be our central element. And that's true. Okay, so our central atom here will be phosphorus. Okay, and now you know that things like phosphorus and sulfur can have these expanded octets, and this is an example of that. So just draw your chlorines out, same way you would if this was methane, CH4. Okay, but I just draw them evenly, space them. Okay, and then put a single bond. Fill in your lone pairs. Always remember to fill in your lone pairs. If you don't have the lone pairs here, this is not a correct structure. So even though a reasonably good, skilled chemist or knowledgeable chemist could know that there's probably lone pairs there, it would not be considered a correct Lewis structure without them. Okay, so always make sure you include them. So like water, if you just drew this for water, this is not correct. Okay, you have to put the lone pairs. Okay, so now if we count up our electrons, we have 2, 4, 6, 8. We have 5 of those, so that would give us a total of 40. Okay, so this is another shape that we can have. So one thing you'll learn in organic chemistry is a lot about the shapes of molecules, something we didn't have too terribly much time to talk about in this class. But so you can sort of see, if you can envision this in 3D space in your mind. Okay, so you have this sort of triangle. Okay, those would all be in the plane. In other words, they would be even, so coming in and out of the board or in and out of the paper. Okay, and then you could say that these 2 chlorines are in the plane of the paper. Or you could look at it so that the chlorines, the triangle of chlorines, are in the plane of the page, and that would make each of these chlorines coming in and out of the paper. Okay, I wish that I could show you this with my hand. It would be much easier, but hopefully you can kind of visualize that. So just remember that when you're drawing these molecules, they have some 3D structure. So something like methane, okay, we could draw it like this. And if you remember back to when we talked about formulas, one of them was a structural formula. Okay, so actually, Okay, methane has more structure like this, okay, where we can put 2 of the atoms, or 3 of the atoms, in the plane, okay, and then we'll have one coming out. And then the way we represent this in organic chemistry is like this. Okay, and these two symbols, so we call these the dash and wedge symbols. So this is a wedge, and this is a dash. Okay, the dashes mean this atom is going into the board. The wedge means it's coming out of the plane of the board. Okay, so this has what we call a tetrahedral shape, and if you maybe played dice games, you might be familiar with tetrahedrons. Okay, that's that sort of triangle, pyramid-y shaped dice or die. Okay, so that's what methane structure actually is like. Okay, so just remember, when you're drawing these things on your page, that they really do have some 3D shape. Okay, I'm going to give you one more example to try, and then we'll be done. Okay, so one more. Okay, I'm going to go with another charged one here, okay, just to give you a little more practice. Calculating charge. Let me find a good one here. I have some examples written down I would usually use in class. Let's go carbonate. Sure, why not? Okay, so CO3, 2 minus. Okay, give this one a try and see what you come up with. Okay, so quickly, I'm going to go ahead and draw out the structure and just talk about it. Okay, so hopefully you came up with something like this. Remember, always put in your lone pairs. Okay, add your charges. Okay, so hopefully you came up with something like this. And the one thing I want to say about this before we end is that we've done a lot of examples where we only had charges on so our overall charge here, in other words, would be 2 minus, which is what's indicated in our formula, and that's correct. But one thing I wanted to say is if somehow we ended up with a positive charge on this carbon, our overall charge would be 1 positive plus 2 negative, which would give you an overall charge of 1 minus. And sometimes when you're drawing molecules, and if you really struggle and you just can't get it right, the answer to your question, if it's a charged molecule, or even if it's a neutral molecule, might be to add a positive and a negative charge somewhere. And that might be the most reasonable structure. And in those situations, again, that's kind of some that come with experience. Something like ozone pops in my mind. That's kind of a difficult one. I can't really think of another one right off the top of my head. But my point is just remember you can cancel out opposite charges when necessary. And there are some molecules that are like that. Okay, so I think that pretty much ties up everything. We're right at our 1 hour mark, okay, which is all the time we really have today. Okay, so I think I'm going to go ahead and end. I hope you enjoyed this lesson. This is one of the funner things to talk about in chemistry. It's something I really enjoy teaching, especially to students that have as much knowledge as you do now and are maybe thinking about going on to organic. If you do, I wish you luck with that. It's a fun class. Like I said, it's sort of like learning a language. Okay? But it's also very sciencey, but it starts to feel very chemistry-y. Anyway, before I say too much, I'm going to go ahead and end this. Good luck with whatever you go on to.